Any questions? If you remember last time we started to talk about designing circuits, digital logic circuits that can add binary numbers, or in other words, we started to talk about binary adders, right? So we discussed how can we design an n-bit adder, a circuit that can add two n-bit numbers to produce an n-bit sum, S or sum, right? And we said if we want to design such circuit using the approach we discussed at the beginning of the chapter, it will be very difficult, especially with large value of n, because the size of the truth table, the size of the number of the input variables will be very, very large. For example, we said if n is 32 bits, then the number of inputs to such circuit will be 64 inputs, right? Because we have two n-bit numbers, and the number or the size of the truth table will be very huge. We will have 2 to the power 64 input combinations, 2 to the power 4 input combination, to 64 input combinations, and this is very huge. So how did we deal with that? How did we approach designing such simple circuit, such basic operation that is found in all computers, in all mobile phones, in all calculators? We looked at the problem from another angle. We said if you want to add, let's say, 4 bits together with another 4 bits, such as A and B, where both A and B are 4 bits, then you are basically adding 1 bit to another bit to produce a sum, and possibly a carry, let's say C1, that is propagated or that is transmitted or that is sent to the next digit or to the next position. Then you add C1 plus A1 plus B1 to produce sum 1, then C2 sum 2, then C3 plus to get sum 3, and possibly there is a carry C4 going out. So we said instead of designing a circuit that takes these two 4-bit numbers and process them all at once, why not to design a circuit that does this, that adds 2 bits to produce a sum and a carry, and then we replicate this cell. We copy this cell, and we connect the copied cells or the replicated cells to each other to produce the 4-bit adder. And this is much easier because when you design such a small circuit, which takes 2 inputs and produces 2 outputs, is much easier than designing a circuit that has 8 inputs, 4 bits and 4 bits. So we started to design such a circuit. So we designed a circuit, if you remember, we called it half adder, which takes 2 bits, adds them to produce a sum and produce a carry. It takes A and B, and we saw how to build or how to design this circuit. It is straightforward. We designed it using the conventional approach that we discussed at the beginning of the chapter. We know the number of inputs, number of outputs, the relation between input and output. So we are able to construct the truth table. Okay, and once we have the truth table, it was straightforward to find the logic expression for both the sum and the carry. However, when we try to use this cell or this small circuit to build, let's say, a 2-bit adder, we discover that it is kind of confusing on how to connect these copies, the copies of this circuit, especially when it comes to working with the carry. Because as we said last time, when we designed the circuit, we designed it for this case where we have 2 bits to be added to produce a sum and a carry. However, the most frequent case is basically the case where we are adding 3 bits. We are adding 1 bit, the carry from the previous bit position to the sum of the 2 bits at this bit position. So we said, why don't we change the way we thought about the problem by designing a circuit that takes 3 bits, A, B, and carry N, which is this carry, which is coming from the previous bit position, and produce sum and C out. And we call this circuit a full adder. Full adder because it adds the 3 bits, including the carry N, while this is called half adder because it does not take into account the carry from the previous bit position. So we designed this circuit, and if you remember, the sum was basically A XOR B XOR carry N, and C out was A, B, or A, C, N, or B, C, N. So we designed this circuit, full adder, that can add 3 bits. So how can we use now this circuit, which is a block? Inside it, we have this circuit. We work with it as a block. Can we use this block to implement this addition operation? Let's say we want to build a 4-bit adder now, instead of a 1-bit full adder. So let's take the same example we had earlier when we talked about the half adder. Design a 4-bit, let's extend it, 4-bit adder, or binary adder, in other words, using full adders only. You don't need anything else to implement or to design or to build a 4-bit adder or any size of adders using the module that we just designed, or that we designed last time. So in order to do that, we need to figure out how many of these units or these blocks do we need. How many do we need in order to have a 4-bit or to implement 4-bit addition? Let's write it again here. A3, A2, A1, A0. We want to add it to B3, B2, B1, and B0. We want to add. So basically, how many additions we are performing when we add these two numbers? We are adding this to produce carry 1, to produce carry 2, carry 3, then C4. So how many full adders do we need? Yes, Sarah, we need 4 because we are adding this, because we have 4 bits. We need an adder for these, an adder for these, an adder for these, an adder for these. And now it is full adder, which means it can add these 3 bits all together, which is different from the case when we worked with half adders. So we need a full adder. We need a full adder. We need, okay, let me make it smaller. We need a full adder, and I want to move it down. Full adder, full adder, full adder, and full adder. So at the beginning, we want to add A0 with B0, and this will give us S0. So if you look, I'm just mapping what I'm doing on paper on what I'm going to do using on hardware, using the circuit. Then we'll get S0. Then we will add A1 with B1, A2 with B2, and A3 with B3. I just changed the position of the inputs, and that is okay as long as I'm labeling the inputs and the outputs. Now, this circuit or this full adder will not only produce S0, it will also produce C1, and this C1 has to be fed into Cn of this. This is C out, goes to Cn. This will produce S1, and it will produce also C2, which has to be fed into the carry in input of the next circuit or the next block. This will add C2 with A2 with B2 to produce sum 2, and the same thing for here we have C3 to produce sum 3, and here we have C4. Of course, if we are talking about 4-bit addition, this is our result. This is our result, and this is not part of the result, but it is usually available to you. You need to make it available to the users of this circuit in order to check for something that we'll talk about shortly, which is the overflow. So this is our result. This is our result, the sum. And the carries are chained, or they are connected. So you look here, this is connected to this one. So this is happening here, this is happening here. This is C out, this is C out, and this is C in, this is C out. Okay. Now, if we look carefully here, this is also Cn, which is an input, right? Which is an input. What is this input? What to put on this input? Should we leave it like this, floating? When it comes to connecting this circuit, can we leave this input floating without being connected to anything?
No.
No, we can't do that. This is very important in digital logic circuits when it comes to actual hardware realization. When you build the circuit, if you have some inputs that you don't need, you don't use, you can't leave these inputs unconnected. You can't leave them floating, not connecting to anything, because this means that you don't know the input value. The input could be 0 or could be 1, depending on the level of interference that is coming into the circuit. So what is the solution if I cannot leave any input floating? Is basically the solution is to connect or to specify the value of this input, or to put the value of to set the value of this input to a neutral value. In other words, a value that does not affect the operation of the system. So what is the value that I can put here? What value can I put here in order to not affect the operation of this full bit adder?
0.
0. I can put 1 because 1 will be added to this, will be added to A and B. But actually, I am not adding anything. The carry into this bit position is what? Is 0, right? There is no carry. There is no previous bits before this bit position. So the carry into this bit position is also 0. So this is very important, and not only for the adder, for any logic circuit that you build. If you have one or more inputs that is not used, you can't leave this input not connected. You need to connect it to 0 or to 1, such that you don't affect the operation of the system. In our case, it is addition, and if we want to have addition, we need this input to be set to 0. And we know that 0 is the neutral value for the addition operation. In other words, it does not affect the addition operation. Okay? Now, this is a 4-bit adder, and usually it has people who work in digital logic design or design logic circuits, they give it a name. They call it carry they call it ripple carry adder. This is called ripple carry adder, RCA. Or some people, they call it carry propagate adder. Carry propagate adder. Because why do they give it a name? Because there are other types of adders. You can design your adder in a different way. And if you are interested, look for example, there is something called carry look ahead adder. Carry look ahead adder, which is another way to implement addition. And the advantage of such CLA, carry look ahead adder, is basically it is faster in producing the result than such adder, than the ripple carry adder or the carry propagate adder. Okay, but this is a topic that is discussed in other courses. If you are computer engineering or computer science, you will be introduced to this carry look ahead adder. Okay, there is a dash here. Carry look ahead adder when you take computer organization course. Okay, but I need you to be familiar with this or this, either carry propagate or carry ripple carry adder. And okay. Now let's assume that we want to design a bigger adder. Let's say 8-bit adder. How can we do it? If we want to have a, let's say, 8-bit adder, what can we do? We can do the same trick, right? We can do the same trick where we bring 8 copies of these full adders and we connect them in the same manner. But now we have the inputs are 8 bits. So C4 will go to the 5th full adder, then the 6th full adder, 7th full adder, and 8th full adder. Okay, it is the same. Or what we can do, and this is usually what is usually done, is basically we design the base unit. For example, here in our case, what if I just put all of these into a box like this? So I designed the 4-bit adder and I put it into a box to become something like this. This is 4 bits, which is the sum. And I have here input 4 bits, input 4 bits. And I call this is A, this is B, this is sum. And this is, let me exclude the 0 out because I will need it later. So this is an input. I have here Cn and I have here C out. So I put this in a box. So it is a black box now. I don't care what is inside, but I know this is a 4-bit adder. This is a 4-bit adder. Can I use such block to design bigger adders? For example, if I want 8-bit adder, what can I do? I just can bring 2 copies of this. I bring 4-bit adder and another 4-bit adder. So I have here sum, which is 4 bits, 4 bits. Here we have Cn, C out, Cn, C out, and we have here input A, which is 4 bits, input B, which is also 4 bits, same thing here and here. And we have C out. And what I want to do, I want to add this. I want to add numbers A7, A6, A5, A4, A3, A2, A1, A0, which is 8-bit number, to B0, B1, B2, B3, B4, B5, and 7. So, but I don't have an 8-bit adder. I want to design it using 4-bit adders. So basically what I should say that add these 4 bits together, then take the carry from it and add it to the sum of these two to get sum 7 through sum 4. And here you get sum 3 through sum 0. So how to do this here? Here, simply, if you look here, what should I input here? A3, A2, A1, A0. And here we will have B0, B1, B2, B3 to get sum 3, sum 2, sum 1, sum 0. And we get here sum 7, sum 6, 5, and 4. And of course here the input carry is 0, so we have to put this to 0. And the carry out, which is C4 here, is going into the next 4-bit adder, which is C4 here. And here, what we input, A7 through A4, here B7 through B4, and here we get C8. The carry out of here is C8. It is going into position number 8. Here, this is position 7. So this is going to position number 8. So now this is a 4-bit adder and another 4-bit adder connected to implement an 8-bit adder. And this is how do they usually design big circuits. They start with the small circuits, they build the basic operation, then they replicate it, if possible, of course. Then they replicate it, they put it in a bigger block, then to implement a bigger block that is bigger than this bigger block, they just replicate this big block, and so on. So let's assume if you want to have 16-bit adder, you want to implement it using 4-bit adders, you get 4 of these 4-bit adders, okay? Or you design this, you put it in a box, and to implement 16-bit adder, you just bring 2 copies of this 8-bit adder, and so on. So this is very important concept. If possible, we usually, to design big circuits like this, we just design the small one, we replicate it to build bigger one, then we build a bigger block to implement a block bigger than this, we replicate the big block, and so on. All right. So what we did here is an 8-bit adder. Is an 8-bit adder using 4-bit blocks. Or we could have done it using this approach. We replicate, or we create, or we use 8 copies of the 1-bit full adder. All right. Any question?
طيب دكتور،
Yes.
ايش اكثر يعني فعاليه انه اكون كل واحده عندي كوبي واحده ولا اعمل مثلا 8 بت ادر يكون احسن مع بعض ولا كل نفس الشيء؟
هي في النهايه هي نفس الشيء، بس انت الك كديزاين لو انا يعني بدي اروح اسوي let's say I want to build an 8-bit adder، تمام؟ بدي اروح اشتري غالبا الفول ادر هذا موجود. You can buy it as an IC, as an integrated circuit, which is easier to bring 8 ICs that each of which contain 8 full adders, or if I can find an IC that has 1 4-bit adder. It will be easier to work with 2 blocks or 2 pieces than working with 8 pieces, or with or wiring 8 pieces. So I forgot the number of the IC, but there is an IC. There are ICs out there in market that contain adders, 2-bit adders, 4-bit adders, and let's say if somebody can tell me next time a number for some IC that contain 2-bit adder or 4-bit adder or whatever, an adder, it will be, I will give him 1 point bonus. Okay, search, do some search on Google next time, not now. Next time, give me a number for an IC that contains whatever size of adder. Okay, 2-bit, 4-bit, there are many out there. So search for them, look at the data sheet and give me the number of that IC. Okay. All right. Let's go to the next type of circuit, to the next circuit that we want to design, which is related to the adder. And basically, it is the binary subtractor. Binary subtractor. So this is it will be section 4.6, binary subtractors. So we designed in section 4.5, we designed a circuit that can add any two n-bit numbers, 2 n-bit numbers. How about now the sister operation, which is subtraction? Subtraction. We want to design a circuit that can subtract 2 n-bit numbers A and B to produce difference, or D. D is the difference, where D is basically A minus B, which is also n-bit. So this is called an n-bit subtractor. This is called an n-bit subtractor. We want to design such circuit. How to do that? We can follow the same approach, where we design a circuit that subtracts 1 bit A minus 1 bit B to produce a difference, a 1-bit difference D, and a borrow. Why do we need to produce a borrow? In order to connect such a circuit to other circuits to implement bigger subtractors. The same that we did in the addition case. We designed a 1-bit adder, right? That produced a sum and a carry. And the carry was produced in order to connect this circuit to other copies of the circuit to implement bigger adder. However, do we need to do this? Do we need to start from scratch? Do we need to start from 0? Where we design 1-bit subtractor? We don't have to. We don't have to reinvent the wheel, because we know that subtraction is basically can be done using addition, right? We know that D equals A minus B is essentially A plus minus B, right? And we talked about this in chapter 1, if you remember, when we talked about sine 2's complement and sine 1's complement. We said we can perform subtraction between 2's complement number by basically performing addition between the first number and the 2's complement of the second number. So we don't have to design this circuit from scratch. because we already know how to know the circuit that adds two numbers. Okay, and we can use this circuit to subtract the two numbers by basically adding the first number to the complement or the two's complement of the second number. And why I'm saying two's complement, because we said two's complement is the approach or the most common approach that is used to represent negative numbers in digital systems. So this is the basic idea of subtractors. If we understood adders, then we can use the adder we designed earlier in order to implement subtraction. And how to do that? Let's look at some example design a 4-bit subtractor. 4-bit subtractor. So instead of starting from scratch, we say, okay, I want D equals X minus Y, for example, where X is a 4-bit number and Y is also a 4-bit number. And I want to do this. I want to produce or to design this circuit. So I say this is basically D equals X plus minus Y. X minus Y. So I say I need a 4-bit adder. So I go and bring the adder I designed earlier, which basically has two inputs, A and B, and each of these, just to be consistent with the book and the slides, it doesn't make a difference. However, just to make it easier, I have A. I said it's not a big deal to change the position of the inputs and the outputs as long as I am labeling the inputs and the outputs. And let me break this down. This is A3, A2, A1, A0. So we have 4 inputs here. And here we have the same thing, B3, B2, B1, B0. Okay, and here we have the sum. Sum 3, sum 2, sum 1, sum 0. And this is a 4-bit adder. And we have here Cn, we have here Cout, which is the block that we designed previously. So this is the block. How can I use this block to implement subtraction? I said basically this subtraction is basically adding A or X here, X, to the 2's complement of Y. Minus Y means the 2's complement of Y. How to do that? Now, if I use this circuit to subtract X, so X, we have X3, we will connect X here, X2, X1, X0. We want to perform X minus Y. So Y is going here, for example. Y is going here. But we don't want to connect Y here. We want to connect minus Y, right? We want to connect minus Y. How to calculate the 2's complement of Y? Minus Y means 2's complement. What is the 2's complement of any n-bit number? How to compute or calculate the 2's complement of any 4-bit number in this case?
No، شو بحسب ال1's complement بعدين بضيف واحد.
Exactly.
ال1's complement هي يعني أصلاً inverter بدها.
Exactly. فإذا if I have here Y3, Y2, Y1, Y0, if I take the 1's complement here and the 1's complement of each bit, I will get the 1's complement of Y, but I don't want the 1's complement. I want the 2's complement, right? How can I get the 2's complement out of the 1's complement? I add 1. And how can I add 1? If I just put here 1 instead of 0. What will happen? what I'm doing here, I am adding X, which is 4-bit here, to the ones complement of Y, right? Because this circuit basically adds this to this. But if the input is ones complement, I am adding A or X to the ones complement of Y to 1. So effectively, I am adding X to the 2's complement of Y, which is basically equivalent to subtracting Y from X to get D3, D2, D1, D0. Okay, so this is much easier than starting from scratch to design the 4-bit subtractor from 0. Okay, to design it from 0, we already have an adder, so we just basically add some stuff outside this block in order to perform the required operation. And this, what we needed to add is basically the inverters. Okay, how about 8-bit subtractor? The same thing. I will bring an 8-bit adder, then I use it in the same approach. Okay.
دكتور عندي السي اوت بكون 0 لانه ما في كاري بالسبتراكتور صح؟
لا out لا راح يكون there will be some value. It could be 0 or 1 depending whether X is less than Y or X is greater than Y. This is now is not C out, it is called borrow.
Okay.
There will be a value here. Okay, and if we want to use this, let's say this can be put in a block, for example, and you call it a 4-bit subtractor, and you can use this block to build larger subtractors. So you can build an 8-bit subtractor like this. You bring 2 copies of this, then you connect the borrow out into the borrow in. The same thing that we did in the adder. Okay, so if I put this in a block, I can build an 8-bit subtractor. I'm sorry, I need to put the inverters inside like this. So I just feed X, Y, and it will do the subtraction. And if I want to build 8-bit subtractor, I bring a 4-bit with 4-bit, and the connection between this and this is basically the borrow. Okay. All right. So this is about subtraction. Any question?
دكتور
أيوة.
عندي لو سمحت سؤال هنا خطر على بالي، هو عن البارت اللي قبل لما كنا نسوي addition.
Yes, go ahead please.
لما يطلع لنا C4 حكيت إنه it's not part of the answer, right?
Yes.
But doesn't that mathematically change يعني من
Yes.
ناحية
This is what I'm going to talk about now.
Oh, okay. تمام.
Okay. Okay.
Yeah, thank you.
Yeah. So this is very important question. Thank you, Jumana. And this is the topic of our short section that is next, 4.7, which is related. It's not about designing a circuit. It is just a concept related to the 2 operations we discussed so far, addition and subtraction, which is overflow. Overflow. And this is very important concept when it comes to designing arithmetic logic circuits or logic circuits that perform arithmetic operation. Now, when designers design arithmetic circuits that are inside the CPUs, they are usually limited, or they usually specify the number of bits to work with. For example, in our case, previously, we said, let's design a 4-bit adder. Now, this adder or this circuit that we designed is only capable of adding 2 numbers. Each of these numbers is 4 bits. These two numbers cannot be bigger than 4 bits. Okay, and the result is 4 bits. Because the input is 4-bit, the result has to be 4-bit. Now, what if we add two numbers, A and B, and the sum requires more than 4 bits? This case is called overflow. It means that the result or the size of the result is larger than the size of the numbers that the system works with. The system originally works with n-bit values. Now, if the result requires a value that requires more than n bits, then this implies that the system cannot cope with, cannot deal with such value because its size is greater than n bits. And this is called overflow. This is called overflow. In other words, the system cannot understand, they cannot represent this result. And this is what is meant by, let's say, it is a 32-bit CPU. When you talk about 32-bit CPU, 64-bit CPU, this implies that this CPU can, let's say, add two numbers. The size of each of these numbers is 32 bits. So if you add two 32-bit numbers and the result requires 33 bits, then the system or the CPU should give you an overflow. And this is what happens in your calculator when you, let's say, add two very, very, very large big numbers. Sometimes your calculator gives you E, in flipped E, right? And what do you understand from this flipped E? Is the answer infinity? No. The answer is there is an answer, but your system or your calculator cannot represent this because it is limited to 16 bits or to 32 bits. It cannot work with numbers bigger than this. So this is very important. Overflow is basically overflow occurs when the result of any arithmetic operation cannot be represented using the available bits. So if you design your system to be an n-bit system and you perform some arithmetic operation and the result of this arithmetic operation requires n+1 bits or 2n bits, then you cannot represent the result because your system is n-bit. So what do you have in this case? You have what we call overflow. And in this case, if you have an overflow, if your hardware results in an overflow, you need to tell the user that there is an overflow. You need to tell the user that there is a problem. So it is very important to be able to detect, we need to detect overflow. Let's say if we designed a circuit that can add two numbers, then we need to be able not to perform the addition only, but we need to tell the user whether the result is correct or not, whether the result can be represented using the available n bits. In other words, we need to detect whether there is an overflow, and we want to tell the user that there is an overflow or not. So usually most circuits, they come with another or additional output, which is called overflow output. And this output is basically set to 1 whenever the result is not or does not fit into the available n bits, Otherwise, this output is set to 0 to indicate that there is no overflow and the result is stored in the n bits. For example, here the n bit sum is correct. The result is correct. Let's, for example, consider this case. Assume that you have 4-bit numbers. You designed a 4-bit adder. So you have 1, 1, 0, 0, 1, 0, 0, 0. And you added these two numbers. So the result will be 0, 0, 1, 0, and there will be a carry. But this carry cannot be used as part of the result because you designed your system to be 4-bit system. So it is there when you perform the addition, but you cannot use it as part of the number because you have 4 bits only to represent any number. This is the maximum capacity of the system. This is the maximum width of the data. We call it width, data width, the width of the data. So this will be ignored. If we ignore this, the result is not correct. It is 4. If you assume these numbers are unsigned numbers, this is a 12 and this is 8, and the result has to be 20. Now, if I'm able to store 5 bits or to use 5 bits, the result is correct. This is a 20. It is 16 plus 4, which is 20. However, I cannot use the carry. I can't use the carry. So the result is basically 4. And I cannot tell the user that the result is 4 because it's not correct. But I need to tell the user that there is an overflow. Don't use this value. This value or this result is not correct. So I need to know, I need to detect overflow. I need to be able to detect overflow. So this is the topic of this section, how to detect overflow when it comes to, let's say, addition and subtraction. How can we know that there is an overflow when we perform addition, when we perform subtraction? So we have 2 cases basically. Overflow with unsigned numbers. Of course, when we are talking about addition and subtraction. When does overflow occur? When you are adding, let's say, n-bit numbers to n-bit numbers. You are adding these 2 n-bits to produce some n-bits. How can you know if the result here is correct or not? In other words, how can you tell whether there is an overflow or not when you are working with unsigned numbers? Basically, if you add 4-bit and 4-bit, when there will be an overflow?
إنه يكون الناتج أقل من الرقمين.
الناتج أقل من الرقمين ولا الناتج؟
إنه يعني أقل من يعني إنه أقل من أي رقم منهم، يعني لازم يكون أكبر من رقمين هو.
مش بالضرورة، يعني لو أنا جيت جمعت مثلا هون في هاي الحالة، لو جمعت 4 زائد 2، الجواب بده يكون 6. الآن هذا الجواب, this number is bigger than the 2. Does this imply there is an overflow? لا.
لا، ما هيك بكون صح. أنا قصدي إنه لما يكون مش أكبر من الاثنين بكون في overflow.
Okay, yeah, okay. What Asim is saying that if the number that we get here is less than any of the 2 numbers, then definitely there is a problem, because if you add 2 numbers, you can't get the answer to be less than the 2 numbers, right? So in order to detect whether the result is correct or not, we need to design a circuit that takes these 4-bit numbers and compare them to these 2 4-bit numbers. However, this is very difficult. We can have another or a simpler approach to detect whether there is an overflow or not. Basically, if you add 2 numbers to get another number, if this number has to be of the same size as the input numbers, then the easiest way to detect whether there is an overflow or not is to decide whether you need an additional bit to represent your result. In other words, if there is a carry, which is, if these are n bits, then this is Cn, which is the carry going into the n bit position, which is not there. Now, if this carry is 0, then the result that you added, that you obtained here, can fit in these 4-bit numbers, in these 4 bits. However, if you add 2 numbers and this carry is 1, and this carry is 1, this implies that you need 5 bits to represent the result. This is, so basically the overflow, predicting overflow for unsigned number is done basically by investigating the carry going into or going out from the most significant bit. If this bit is 0, then 0, then there is no overflow. However, if this bit is 1, then there is overflow. This is much simpler, Asim, than taking these 4 bits and check whether these 4 bits, the value in these 4 bits is less than these two, any of these 2 numbers. The circuit to do the comparison is more complicated than just investigating this one bit, which is the carry out of the most significant bit in the 4 numbers. Okay, so this is how to detect overflow. So if you are working with unsigned numbers, in order to determine whether the result is correct or not, whether there is an overflow or not, you need to investigate, or you need to look at the carry out of the most significant bit only. The carry out of the most significant bit. All right. Okay. Now, how about signed numbers? Is there a difference in detecting overflow when it comes to working with signed numbers? Overflow in signed numbers, or detecting overflow in signed numbers. You're adding a set of numbers, or 2-bit, or 2 numbers, each of which, let's say, is 4 bits. However, the numbers now are signed. What do we understand when we say the numbers are signed? We know that this is the last bit, or the most significant bit is basically what? The sign bit, right? It indicates the sign of the number. So if this number is positive, then this bit will be 0. If this number is negative, this bit will be 1. This bit will be 1. So now, if we add, let's say, 2 signed numbers, if we add 2 signed numbers, and we are talking about 2's complement signed numbers, how did we do that? What we did, if you remember in chapter 1, we add this bit to this bit, this bit to this bit, this bit to this bit, and even the sign bit, we add the bits together to get the sign of the result. Now, if I tell you I added 2 signed numbers and obtained a result, can you tell me whether there is an overflow or not?
دكتور، نطلع على الرقم، يعني مثلا لو اللي فوق نيجاتيف واللي تحت نيجاتيف، يعني حسب شو بيكون الريليشن بين ال 2 numbers، إذا positive أو positive ونيجاتيف.
Exactly. يعني لو جينا حكينا, because when we add sign numbers, we also add the sign. There is a problem if I add, let's say, a positive number and a positive number, and I get a negative number, right? How can I get a negative number if I add positive number with positive number? The problem happens because we add the sign bit to the sign bit along with the carry that comes into the sign bit, right? Because we add this bit to this bit, we get this bit, and there is a carry. We take it, we add it to the sign and sign. So let's assume the addition of these 2 bits resulted in a carry that is 1, this one will be added to 0, will be added to 0 to get a 1. Okay. However, if I added positive to get a positive number, then there is no problem. And how do I get a 0 here in the sign bit of the result? If I'm adding the carry, the sign, the carry into the sign bit has to be 0, right? Because 0 plus 0 plus 0 equals 0. So in order to detect overflow in sign number, we need to investigate all the cases in which we have overflow or we don't have overflow. For example, I will consider this. Or before I consider this, I just want to stress this point. When we add sign numbers, we also add the sign bits. We treat the sign bits as normal bits. So we add them in addition to adding the carry into the sign bit. So this is the sign bit. So if we want to detect overflow in sign number, we need to investigate all cases for adding the sign bits of the two numbers. And we know now that there is no overflow. If we add positive number with positive number, we should get a positive number. If we add a negative number with a negative number, we should get a negative number. Otherwise, if we add a positive number with a positive number and we get a negative number, then there is a problem. There is an overflow. All right. So how to design such a circuit? So let's take the 4 different cases. Let's assume I have a number and this is its sign bit, which is 0. And I have a number which is its sign bit, which is also 0. So I am adding positive number to a positive number. And if there is no overflow, then I should get some number, and the number is, or the sign bit of the result should be also 0. So in this case, there is no overflow, right? If I add a positive number to a positive number to get a positive number, then there is no overflow. Now, if I'm performing this addition, how can I get a 0 here if I am adding these two numbers? The carry into the sign bit should be 0, right? Because if I add some bits here and the carry is 1, I will get here a 1. So in order to have no overflow, when you add 0 and 0, the carry also into the sign bit should be also 0. Okay, and accordingly, the carry out should be also 0. So in this case, there is no overflow. And in order to have this case, the carry into the sign bit should be 0, and the carry out of the sign bit should be also 0. So if I'm talking about n-bit number, this carry, we call it, if you remember, Cn-1 equals 0. And this is Cn, which is the carry going into the n-bit position. This is the carry going into the n-1 position. So in this case, there is no overflow. The same case, when you add, let's say, negative number with some other bits to get some bits and a negative number. How can you get so this case? In this case, there is no overflow because you are adding negative number to a negative number. How will this happen? How can you get a 1 here if you are adding a 1 and 1? 1 plus 1 is 0 plus carry and carry, right? So, but remember always that we don't add the sign bit to the sign bit only. We are adding the sign bit to the sign bit to the carry into the sign bit. So if I want to add 1 plus 1 to get 1, then definitely the carry into the sign bit has to be 1. Because 1 plus 1 plus 1 is 3, which is 1, and there is a carry out. Cn will be out. Okay, so this is very important. When we add sign numbers, we add the sign bits, but we add them along with the carry in the sign bit. So negative plus negative should be negative if there is no overflow. But 1 plus 1 will give you 0 here. Right? How to change this 0 to 1? How to have this 0, 1? The carry into the sign bit has to be 1. And accordingly, the carry out of the sign bit will be 1 as well. Let's take the other cases. If you add 0 plus 0, but you get 1 here, which means you add a positive number to a positive number, you get a negative number. How can you add 0 to 0 to get 1? This only happens if the carry into the sign bit is 1 and the carry out of the sign bit is 0. Because 1 plus 0 is 1. So this means that you added these bits to these bits, but you get a carry which is fed into the sign bit, and in effect it will change the sign. So here we have overflow. There is overflow. The same case when you add a negative number and a negative number to get a positive number. 1 plus 1 is 0. Okay, and this is overflow because you are adding negative number to negative number, you got a positive number. But you don't add this to this only. You add it to Cn minus 1, the carry that is coming from the previous bit position. And in order for this to happen, this has to be 0. So 0 plus 1 is 0. Okay, and if this is the case, the carry out of here is Cn is equal to 1. And in this case, there is overflow because you're adding negative to negative, you get a 0, positive. And how do you get 0 here if you are adding this to this to this? Basically, the carry into the sign bit has to be 0, and accordingly, the carry into out of the sign bit should be 1. Now, how about other combinations? For example, adding a negative number to a positive number. Is there going to be an overflow if you add a positive number to a negative number?
لازم نعرف قيم النمبرز عشان نعرف إذا في overflow or not.
بس لا مستحيل يصير overflow.
Exactly, Asim, thank you. When you add a positive number and a negative number, there is no way that you get a number that does not fit in the n bits. The number will be always between the two numbers, right? So we don't need to consider these two cases. The only cases that we need to consider for addition is basically these 4 cases. So now we want to design a circuit that tells us whether there is an overflow or not when we add sign numbers. And how to do that? Basically, we know if you look at the cases we discussed, the inputs to this circuit will be C sub n and C sub n minus 1. These two values control or decide whether the results is correct, the result is correct or not. So this is an overflow detection circuit. It has 2 for sign numbers. So this is overflow detection for signed numbers. So how to design this circuit? Simply, very simple circuit, Cn minus 1, 2 bits, the inputs, and the overflow output, 0, 0, 0, 1, 1, 0, 1, 1, like this. So now, if the carry out of the most significant bit is 0, and the carry into the most significant bit is also 0, is there an overflow? No. So this is 0. If the carry is, if Cn is 0, Cn is minus 1 is 1, which is this case, there is overflow. So there is overflow. 1, 0, which is this case, there is also overflow, and 1, 1, which is this case, there is no overflow. So if I ask you, design this circuit that detects overflow in signed numbers, what is this circuit?
XOR.
It is XOR. So basically, the overflow is Cn XORed with Cn minus 1. So simply, when I design the adder, I just add this component to detect overflow. I take the carry into the most significant bit, or the carry into the sign bit, which is this value, XOR it with the carry out of the sign bit to obtain overflow. So this takes us back to Jumana question. Why were we concerned with Cn, or the carry out of the most significant bit? It is important in detecting overflow in unsigned numbers and detecting overflow in signed numbers as well. And in the signed numbers case, we are also concerned or interested in Cn minus 1, or the carry into the sign bit, or the carry into the most significant bit of the two numbers. All right. Okay, let me just turn on the camera. Yeah, there was a problem with the software. Okay. So again, this is what Jumana asked about. Why did we take? Why we were interested in Cn when we designed the adder? Basically, because it is used to detect overflow in signed numbers and unsigned numbers. Okay. Any question? All right. So this is how to detect overflow in addition. How about detecting overflow in subtraction? Is there a difference? Actually, it is the same, because we just said that subtraction is addition, right? So if you are doing subtraction, you are basically adding a number, the first number, to the negative of the second number. So it is the same case. Subtraction is essentially addition. So detecting overflow is just the same. Okay. Now, the last thing before we go, I need maybe 7 minutes, which is section 4.8. Binary adder subtractor. There's some lag, I know. Now in one section we discussed how to design an adder. In another section we discussed how to design a subtractor. Now these are two simple operations that are usually found in most computers, in all calculators, and so on. Now, if we are talking about huge or large or big size numbers, for example, 32-bit numbers, and you want to have a system that can add 32-bit or it can subtract 32-bit. So if somebody asks you to design a system that can perform these two operations, it adds 32-bit to 32-bit, or it can subtract. How will you design this system? Basically, you will say, okay, I will design a 32-bit adder using 32 full adders, or using 8 4-bit adders, or using 8 4-bit adders. or 4 8-bit adders, and so on. The same thing for the subtractor. We know how to design this, we know how to design this. However, if we ask this question, is this cost effective for these two simple operations? Is it effective to design this as a separate unit than designing this unit if we know that we can perform addition, subtraction from addition? Is it cost effective to have hardware for this and hardware for this? If we know that we can use this to perform this. And that's why here the title, adder, subtractor. Can we have a hardware, one piece of hardware that can both add and subtract? We know how to build this. We know how to build this from this, right? We know how to build this from this. But can we have one unit that we can control to perform addition or subtraction? In other words, can we use an adder that can be used for addition sometimes or subtraction for other times? In other words, we need the adder to be, the hardware to be configurable, to be used as an adder or as a subtractor. This is straightforward. If you remember the 4-bit subtractor, how did we design the 4-bit subtractor? This is the 4-bit subtractor. We had 4 bits A, we had 4 bits, for example, here B. What we did here, I will just break these. We have B, 4 bits, B3, B2, B1, B0, right? So what we did to have the subtractor, we have 1 here, and we put the inverters, right? Here. We had X, then if you remember Y3, Y2, Y1, and 0. This is how to use the adder as a subtractor. Okay, if I want to use this circuit as an adder instead of being a subtractor, what are the changes that I need to do? Basically, I need to remove these, and I need to change this back to 0, right? So if I do this, this circuit will add X to Y. But if I bring back the inverters and I change this from 0 to 1, then I can make this circuit a subtractor. And this is a big save. You will save a lot if you are able to do this. If you are able to change the setup such that if you need to perform addition, you make this 0 and you remove the inverters. If you want to use it as subtractor, you make this 1 and you put back the inverters. If you can do this, then you don't have to have a separate unit for addition and a separate unit or hardware for subtraction. How to do this? This is the idea. How to do this? How can we use this circuit to perform both addition and subtraction? We need to control these inputs. As we said, if it is addition, then we need a way to remove the inverters and to make this input 0. If we want to use it as subtractor, we want to put back the inverters and make this input 1. And how to do that? Basically, we need some hardware here that is configurable. In other words, that we control. Let's say we have control signal M, or the mode signal. And this signal or this input specify whether the operation mode is addition or the operation mode is subtraction. So M equals, if it is 0, then it is addition. If it is 1, then it is subtraction. For example, I'm designing the circuit. I can specify it the other way around, 1, 0. But this is the approach that is discussed in the textbook. So if this bit is 0, I want to perform addition. If this bit is 1, I want to perform subtraction, which is the same value that has to be fed into Cn. Now, if m is 0, I want to feed here 0 in order to perform x plus y. But if m is 1, I want to perform x minus y, and this has to be 1. What is left here is how to control the inverters here. What circuit or what hardware can I place here such that when the M signal is 0, I want to take Y0, Y1, Y2, Y3 as is and feed it here. In other words, there are no inverters here. Okay. Yes, it keeps. Okay, so this is, oh, there is a problem with Zoom today. But I need to finish this. I need to finish this because I already started it. Is it working? There is a lag. Let me try to start this program. Stop. Okay, so we need to control what is going into these inputs. As we said, if it is addition, we need here 0, and we need y to go as is to b. Now, if it is subtraction, we need to feed 1 to the Cn, and we need to put back the inverters, or not necessarily the inverters physically, but the effect of the inverters. We need to flip it. So if I tell you what to put here in order to control whether Y0 is complemented or not, based on M. So if I ask you, design a circuit that takes M and takes Y0 to produce some output, let's say B0 here, such that if M is 0, then B0 is Y0. I don't want to invert it, so it is 0, 1. And if M is 1, I want to complement Y, because I am performing subtraction based on M. So Y will be complemented. What is this circuit that complements Y0 to produce B0 based on M? So now if M is 0, we are not complementing Y0. If M is 1, we are complementing Y0. What is this circuit? What to put here? Yalla ya Asim. What is this circuit? What is the gate that has 2 inputs and has this truth table?
اكس الاكس برضه نفسها الاكس ار
XOR. شوف قديش ال XOR important. So basically B0 is M XOR Y0. So if I place an XOR gate here and I take Y0, feed it here, and then we have here M. Then I can control whether B0 is Y0. Here B0 equals Y0, which means addition. Here B0 equals Y0 bar, which is the one's complement. The same thing for what? For the remaining inputs. So if you take M here, 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 and this is Y1, Y2, Y3. Now this circuit can produce 4 bits, which are either the sum or the difference. Based on what? Based on the value of M, which is the mode, which is the mode control or the mode bit. And this is how they do it when they design CPUs, microprocessors. This is how they implement addition and subtraction. It is 1 unit, but it is controlled by some input in order to specify whether it is an adder or it is a subtractor. Okay, so you can put this. This is X. You can put this in a box like this, where you only see the inputs and the outputs, and we call it binary adder subtractor. Okay, and you can design it, you can sell it to others as a black box, and you tell the user that this is X, this is Y, this is sum or difference, and this is the mode. And you tell the user how to use it. If M is 0, then you are basically adding X to Y. If M is 1, you are basically subtracting Y from X. And it is very important to know this. Why did I do this? Because I wanted to have a circuit here that based on M, it either keeps Y0 as is, or it complements Y0. So this is how I designed it. This is very simple design, and it came up to be an XOR gate. And if you remember, this is what I said when we discussed the XOR gate. We said it is very, we will encounter it a lot. We saw it in overflow detection. We saw it in the adder, one-bit adder design. And here you go again. We needed it to design a circuit that can be controlled either to pass Y0 as is, or to complement it or compute the ones complement of Y0. All right. Okay. Any questions? Tamam. Okay. Now I just want to make to remind you that Friday you need to submit homework number 2 using the same approach through e-learning. You have to take photos of your solution, then put them in one file, the PDF file, and upload it using e-learning. Another thing is quiz number 3 will be what? Monday or Wednesday? What do you prefer? Monday or Wednesday?
Yeah.
What?
Wednesday.
Wednesday. Okay, next Wednesday, which is what? اليوم 8, so 16/4 we will have our third quiz. It will be on chapter 3. It will be on chapter 3 on e-learning.
15.
لحظة شو اليوم؟ اليوم 8 sorry 15 yes 15 I'm sorry.
chapter 3 كلها؟
Chapter 3 yes which is came up يعني which is very important انك تدرسه في المرحلة الحالية. إذا ما درسته يعني كل اللي عم نحكي فيه بالديزاين يعني على الفاضي. صحيح؟ Okay. And I need to remind you also about Logisim. I think some people حاولوا إنه ينزلوه which is straightforward. حاول إنك تنزله لأنه probably زي ما حكيت homework 3 will contain a problem, simple problem on Logisim to get you familiar with it and get you to use it. ساعات مكتبية جود let's see شو اليوم اليوم الأربعاء how about tomorrow at let's say 3 o'clock office hour tomorrow اللي هو 9/4 April 9th at 3 p.m. تمام? I will send you a link. I will send you a link today or tomorrow for the office hour meeting. I need to create a meeting for this date and time. Okay, prepare your questions. وأنا بحاول أجاوب قدر الإمكان. بكون عندنا ساعة من 3 ل4. We have an office hour to answer your questions. تمام? All right, so see you on Monday إن شاء الله. يعطيكم العافية.